So our next speaker is Professor Xiaoqi Yang, and he's from also the Hong Kong Polytechnic University. And the title of his talk is Extended Newton Methods for Multi-Objective Optimization, visualizing function technique and convergence analysis. Okay, Professor Yang, please go ahead.
Yeah, thanks, Fusen. Good morning, everyone. Now I'll talk about the Newton method for the multi-objective optimization problems. This morning, Ansen talked about Newton methods for generalized equation using more advanced methods. Metric irregularity. Here I'll use more classical approaches. They joined work with Yaohua Hu from Shenzhen University, Chong Li from Zhejiang University, Jinhua Wang from Zhejiang University of Technology, and Carissa Yu from Hansen Management College. Here it says the Hansen Management College, but now it is the Hansen Managed University, new university in Hong Kong. So that's briefly the outline of my talk. I'll say literature review and the convergence analysis, and about the convergence criterion for the three kinds of the convergence. Then one thing is about the estimation of the convergence radius. That's the main purpose of this talk. Here we can estimate how large this convergence regions could be. Right. Then we will apply to a classical condition which are used in the convergence analysis for the Newton method. This is a problem we're going to study. So this is a multi-objective optimization problem. So we have a criterion M objectives. Then U set here is an open set. That means this problem basically is unconstrained problem, right, with no constraint. So we are assuming here the objective functions are twice continuous differentiable and convex functions. Right. So twice continuous differentiable ability is needed because we are talking about the Newton method. So we're also talking about the convex function, so we don't worry about the local minima or global minima. All right, so for the multi-objective optimization problem, then you can talk about the Pareto optimal or weaker Pareto optimal or local or Pareto optimal. So there are several kind of solution which depends on the ordering cone. It's here we only use the simple one, which is the ordering cone is the positive authent. Right. Now there are basically two types of the methods that can be used. The first one is the scalarization method. Right. In this method, so one major issue here is the choosing the parameters or choosing the weights. So for to get the particular points or to get all the efficient frontier, then we need to choose the parameters, the weightings in order, which is kind of in simplex, right? Which is summation is equal to 1 and the non-negative. Right? So in that case, we need to choose. Now, how to choose the those parameters, of course, is a technique. Then in that way, once you have choosing the parameters, then you can transform the problem into a single objective optimization problem. All right, so that's the scalarization method. The second one here is the descending method. So in this case, no weighting is needed. Then, but what is needed here? But because you have the weighting is different weighting given different Pareto optimal. But if here we don't have weighting here, now how do we find out the whole efficient frontier? Because in multi-objective optimization, one important issue is to find not just one Pareto optimal, is to find out so whole efficient frontier. So in this case, in the context of the descending method, so what we need to do here, so basically is you need to use different initial points. All right, so you start from different places, so that's finally you can plot the whole efficient frontier. All right, so there are quite a number of the descendant methods. So one I like to mention here is Newton method. That's what we're going to talk about. So it's by Flingen, Jormont, Schroeder in 2009. So that's a paper we're going to refer frequently. Then there's another method I'd like to mention here is extension of the proximal point method by the Bonal and the issue Schroeder 2005. They use the Euclidean distance to approach this proximal point method. We did some work with my co-authors in 2011. We used Bergman distance instead. Right? So we also did the convergence analysis. Then talk about the Newton method. Then we can have the so for equation a system of only one equation here or somehow. So that's the basic Newton iterative scheme is like this. So we have this one here. So that's iterative Newton schemes. And we need to find out this the gradients and the inverse or something like this. So that's the typical the Newton iteration for solving the problems. Then Newton methods is well known, good for the quadratic convergence rate. Right. So that's good thing of the Newton method. Then briefly there's two classical results. So that's one is Kantorovich theorem. So that's proof the quadratic convergence under some condition in regarding to the initial point. Then the second one here is the small point estimate theory. So basically, is how do we guarantee that the initial points we choose is kind of good approximation of the solution we want. All right. Then there's another technique used in the Newton method, proved by the Professor Xinhua Wang. Then it's kind of called the L average Lipschitz condition. All right. So this condition is the one that we're going to use. So instead of the classical Lipschitz condition, we will use the L average Lipschitz condition. All right, so what it is. Now another one is the majorizing function technique. All right. So this here, the Newton methods, the scheme for the from the Flegen, Drummond, and Schroeder in their paper. All right. So basically, it's, what they are doing here is to find the search direction then by solving this minimax problem. All right, so we have here the twice differentiability. Now we have just expand the object function. Then in the second order, then take the maximum of this approximation, and then minimize. Then in that way, we can find out the searching direction S. So this one basically, if you talk about why here is minimax, why here is minimax, because here now we don't have the weighting parameters. So we don't have the weighting parameters. Now, how do we transform kind of multi-criterion objective optimization into the single objective problem? So one possibility here is, instead of you doing the linear scalarization, then you can use this kind of max. You use a max kind of scalarization. So remember, when you have a convex efficient frontier, then which can be kind of touched by the linear function on that side. But however, that convex efficient frontier can also approached by some kind of rectangle curve, right? So you can touch that one. So you can touch that one by the rectangle curve. Actually, one thing here, if you use this maximum here, rectangle approach, rectangle attach, you don't need the efficient frontier to be convex, right? So actually, the convexity is now required for the using this approach. Then we will see how that's probably. So that's just a thought here. So they also use the medium line search to improve the searching results. All right. So this is a scheme proposed by the Flingen's paper. All right. That's the extended Newton method. Theoretically, the searching direction S of X can be found analytically, as long as we have this parameter lambda j of X. Right. So existence of lambda j of X guarantee we can have this analytic expression for the search direction. All right. Then numerically solving that problem in step 2 is now difficult. Remember now the capital F function is convex. Then that minimax problem can be converted to this constraint optimization, which is convex. So that is that convex and quadratic. So in that case, the search direction can be found quite efficiently. Right. I missed the one point I want to mention again. Also, from this Newton iteration here using the minimax scheme, actually this method has also been studied in the book by Elijah Polyak. Right. He studied his problem was the minimax problem. Right. So then he approached the object function, use the second order approximation. All right, so that's in the Professor Polyak's work. All right, then what is the major contribution in the Flingen's 2009 paper? So they basically obtained the so-called semi-local global quadratic convergence theorems. Right. Then what they are major assumption is that they assume the Hessian of the FGA is Lipschitz continuous. All right. So they have three kind of convergence result here. So it's semi-local convergence, local convergence, and a global convergence. We found somehow there are semi-local convergence kind of probably I would say difficult, complicated. We say here they depends a lot of parameters. All right, so that's the semi-local convergence. For the local convergence, what do they have there? They only have existence of the radius. Right. They have the existence of R. Now within the initial point of this R ball, then with the ball of the optimal parallel optimal solution with a ball of R, then they can guarantee the local convergence. So the R is guaranteed to be exist. Right. Then they also have with the medium line search, they can get the global convergence. Then what we're going to do here, we're going to assume, as I mentioned, L average Lipschitz condition, which is kind of a weaker condition. So in that way, we can have more explicit convergence criterion to ensure the semi-local convergence, right? Then second one here for the local convergence, we can exactly estimate the radius. So we can find out how large the radius it is. Of course, it depends on a number of the parameters. Then we also did the global convergence, which we did 2 more here. So instead of the apart from the Amigo, we have a Goldstein and offline search scheme as well. So as I mentioned, we measure. We're going to use in the majorization function technique. In regarding to the convergence, so this is a scheme we mentioned before. So we have this search direction is a solution for that minimax convex quadratic problem. Now have the optimal value is theta of x. Then we can do this Newton step by using this one here. So that's the typical Newton method. Then here we briefly review the Amigo, the line search. So we have kind of 3 types. Amigo row here, then we can, as long as alpha n satisfy the largest one of this 2 to the power 2 negative I, which satisfies this inequality. So that's the alpha being used in the Newton step. Another one here is the Goldstein rule, which apart from this first inequality, then we also need the alpha n satisfy one more inequality here with particular beta 1, which here the beta 1 is between the sigma and the 1 here. Then another one here is Wolf rule for the line search. So again, here we have another inequality, which kind of using the first order approximation of the objective function instead of the just use the function value. Right. So that's the different kind of line search that can be used. All right, so in that case, now we can, that's the basically the Newton algorithm we in our scheme. So again, we have the Newton direction. If it is equal to 0, then we stop. Then we do the line search by 3 types of search scheme here, Amigo, Goldstein, off-road, respectively. Then is once we get the alpha n from the line search, now we can have this Newton iterating. So this is a standard Newton method. So what we're doing here, so this what's new here in this paper here in this work. So this so-called the majorizing function technique. So what we have here is we have a L function. It's a non-decreasing integratable, right? So that's we have this L function here from the 0 to the R. So remember, this R here is an open interval, half open interval here. So in that way, we can find out this integral here. Then because this is increasing function. So this one value here is positive. In that way, this is a fixed value as long as R is fixed. So this is fixed, then we can find the A which is satisfy this relationship. All right. So that once we found the A, now we can use the A. Now we can find out this upper bound of the integration of this RA from this equation here. So from this equation, we can find another parameter RA. Right. So that's what we need in our later analysis. Then once the RA is found, then we can use this equation to find out this BA here. So those are the parameters that that we are using in our analysis, RA and BA. So using this, then now we can define another function here. So this now is real one variable function. All right. So we have the T here now is a real variable function. So what we are going to do here is we're going to apply the Newton method to this one variable function. It's a part of, instead of initially we found for this kind of multi-objective function problem, then now we have a one variable function. Of course, this one has nothing to do with the original problem data. But here now, important here is this L function, which is non-decreasing. So that's why here now we introduce this function here. So as I said, now we're using the Newton iteration to this H function. So now we can find out this T steps here. So with this one, with this T, now we can construct the what we can do here with this T. Now we can find some kind of this RA star 0 for this H of T is equal to 0. So we can find out a solution for that equation. So this is here now for the for this L non-decreasing function. Right. So that's basically part of the majorization function technique. So this is how, of course, the introduction of this L function is kind of tricky. How do you introduce this function? But we can do it for different problem. If you have a real problem there, then this L function probably somehow can be constructed. All right, so this is the introduction of this L average Lipschitz condition. All right, so what do we have here? So we're talking about this for Hessian. So Hessian here, now we say they in the Flangens paper, they use the Lipschitz condition for the Hessian of the objective function. Now here, now for the Hessian of the objective function, now we introduce this so-called L average Lipschitz condition. So now we have introduced this L function. So we now say if this inequality is satisfied, now we say this Hessian function is said to satisfy this L average Lipschitz condition. Right. So this kind of will have integral here. So if the function, the Hessian is is Lipschitz, then this L function can be chosen as a constant. All right. But in general, if we have this L average Lipschitz condition, then you might not can find out a constant, because remember we have this L function which is not defined on a closed interval, which is defined on an open interval. So in that case, this L function might not be bounded. So in that way, so you're allowed able to find out, you're allowed able to prove that this L average Lipschitz condition is equivalent to the Lipschitz condition. Basically, it is weaker. So that's basically the contribution what we are going to have here. So we apply in weaker condition to prove this quadratic convergence here. All right, so that's basically some assumptions that we did in our analysis. So first one here is now, remember now we have this for X in this open set, you have X for the A and R. So as long as we have this triple point here, we assume we have exist of R have this L function, we have this L function here. Then also this second assumption here, this Hessian is positive, and it is the inverse is bounded by this particular A here. Right. So then also we assume, of course, this Hessian is L average Lipschitz property, right, on this open ball is in this open set. Right. So in that case, now we can have this first lemma here. That's conclusion. We can have this bound for this Hessian inverse with this this here. So those are dated in the analysis. All right. So now we come to the local. We come to the convergence results. So first one here is semi-local convergence results. So in this way, what we are doing here is for the semi-local convergence results. So we have a sequence xn generated by our algorithm from our initial points x0. Then assumption here, so F satisfies assumption 2 associated with this x0 and A and that RA star. Remember, this RA star is that unique solution of this h of t is equal to 0. Right. So in that way, we have the initial point. Then now we can say that the whole sequence xn will stay in this ball of the initial point with the radius of this RA star here. Right. So in that way, we have this sequence stay in this ball and also convergence to a local Pareto. Local, I think here is not important because it's a convex problem. So convergence to a Pareto optimal X bar within this closed ball. All right. So in that way, what we are doing here is we are guaranteed that starting from the x0, then we found that the sequence would stay in a kind of a ball of this initial point and also convergence to a Pareto solution. So this is the semi-local convergence. Then we can have this, if the some kind of more condition here, we can guarantee the quadratic convergence here. Right. So that's the semi-local convergence. Then we can also have some conclusion here, and if the so now I go to the another one here. Then the local convergence, again, we have this L function is non-decreasing. Then we have the A star, as you remember, we defined early. Then what we have here, A star, we have R A star, also B A star here. Right? So in that way, we can define all this parameter. So what is the local convergence result here? It is now within a given Pareto optimal. Now we have a quantitative, we have a fixed, we have a exact estimation of the radius of this value here, BA star over 1 plus psi A star here. So this is a quantity that we can estimate from the information of this L average function, this L function. Right. So those parameters can be found. So in that way, as long as the initial point x0 is choosing within this ball, then we can guarantee that the xn generated by the sequence convergence to a Pareto solution. Right. So this one here, so what I mentioned here. So in the Fringes 2009 paper, so they only have existence of the radius, but here we use this L function. Now we can have this exact expression of this radius here. So this is the local convergence. Now we can also have other property here. Then, of course, we also get the global convergence for the 3-line search. Then I go quickly 2 applications. So first one here is the counter-Lorentz type theorem. So they are using the classical Lipschitz condition for the Hessian. So that's basically the Lipschitz condition for the Hessian function here. So in this way, then now we can get the what we can have here. So if you have the Lipschitz condition, then that L function non-decreasing can be chosen as a constant, obviously. So in that case, with the non-decrease function is a constant L which appear here. So also again, we can find RA and BA or all this value here. So in this way, so we can use our majorization function technique. Then we can again prove the convergence results. All right, so that's the kind of generalization of the classical results. So we can have local convergence, semi-local, and the local convergence here. Then also have a global convergence. Then the last one here is the so-called the Smell type theorem. So what is it doing here is they using another condition so-called the gamma condition. So what is the gamma condition here? So gamma condition here is that in a ball, in an open ball, now the 3rd order derivative of the objective function satisfy this inequality here. So what's about here? So there's a gamma, but this denominator here is 1 minus gamma times this distance to the power 3 here. So this is so-called the gamma condition used in the literature. So because of this one, they have a very have a structural property for the 3rd order derivative here. So in that way, we can construct this L function here. We can construct the L function using this structure here on the right-hand side. So as we see here, we have 2 gamma, 1 minus gamma u to the power 3. So in this way, we can use this L function non-decreasing as this. So we can show that this Hessian of the objective function is L averaging Lipschitz function with L defined by this one here. So as long as this way, so we as long as we have a gamma condition here, now we can use our technique, majorization function technique, to prove the semi-local convergence, local convergence, and also the global convergence here. Right. So we can have all this. Again, of course, we can find out those parameters. So we can have a semi-local convergence. We can have the local convergence. All right. So finally, there's kind of there's an example here we constructed. Just use a few seconds here. So the what do we say here? This function is constructed to show that we can, our condition, this L average Lipschitz condition can be applied, but this classical Lipschitz condition is not applicable. Right? So this just one example to show kind of advantage of our results in compare with theirs in the paper. All right, thank you very much. So thank you for your attention. So that's my about my talk. Thanks.
Thank you, Professor Yang. And as this is our final talk in this session, so we have time for discussions. So any questions? Yeah. So I have a question, and that's a very interesting idea, and to solve multi-objective optimization problem in this way. It's very nice and very theoretically beautiful, I would say. And for this L function, so you mentioned that you can choose, case by case basis, or something like that. Yeah, is that right? So for real problems, this L can be chosen in some, some good rule, or how to do this.
Yeah, it depends on the structure of the objective function f1, f2, fn. So as long as I'm not sure if you have a general objective function. Is that so easy to construct the L function for that particular the 1 over 1 minus u to the power 3? That one can be kind of easily to construct the L function. But if you have a general given specific f function, I'm not sure how that L function can be constructed. Probably it's that's the difficult point. As long as you can construct the L function, then the following analysis we have established. But in general, I'm not sure. Yeah.
Okay. So yeah, now we yeah, that's true. And okay. So any other questions? Okay, it looks maybe people are tired. With all these 6 or 5 talks. And okay, so if we have further questions, we can again, communicate with Professor Yang, and using Slack or use other means. Okay, let's thank Professor Yang and all the speakers in our this morning session.